Hello, everyone. This is a problem where we use beam theory to solve for shear forces and bending moment, draw their diagrams, and it's a first simple problem where we have just concentrated loads. So let's dive into it. This is, as you can see, the cantilever beam we have right here, and the two concentrated loads P. There, by the way, this problem I work on it is symbolic, as we can see. So I've all these problems have three steps. The first step, of course, is to solve for support reactions. So we have to isolate the beam. Well, we can see that being a cantilever beam with a fixed end at point A, then we have these three reactions there in the plane. We are here in a 2D plane, and we start solving using Newton's second law. That it's by this time you should know how to use this very well. After we get the reactions, especially we can see the AY and MA, then we go on starting to build a shear diagram based on two things. First of all, we can see that wherever we have concentrated loads, we are jumping up or down where these loads are showing us to go. And then we use this derivative equation that you developed in the class. So basically, we start at point at the left side, and we can see that AY basically it's pointing upward with 2p. That shows us that we need to jump upward in the shear diagram with the same value of AY. And then as we move from this point to the right, we have to look at this equation, and that tells us that the slope of the shear force it's should be equal with a distributed load W of x. For us here in this problem, we have not no such distributed load, so basically it's zero. And this thing tells us that the slope of the shear force is zero, which means it's supposed to be a horizontal line. And I did put here two segments that you can see. So that is because starting from A to B, we see that we have this 2P that we started at point A, and then we draw that horizontal line, meaning that there is no change in that. Everywhere here will be the shear will be 2P. Then as we reach point B, immediately there we can see that we have this external load pointing downward. Again, we apply the same principle. We jump downward this time with the value of P, and we remain with, with 1P here. So then, as we need to move again along segment BC, we look again at that equation, and it's similar like in the first segment. We have the same horizontal line, and that is just no change in there in the shear diagram. And then when we reach point C, again we have this concentrated load that shows us that we need to jump downward. So this is basically the shear diagram, very simple one. And now based on this diagram, we are gonna use we are gonna build a bending moment diagram, which we have it here. So I put here in this slide the free body diagram, the shear diagram, and now we go on to build this diagram. Again, we look at this time at the concentrated moments and this equation, the derivative of the moment. So as we move from left to right. So this concentrated moment, which is counterclockwise, we figure it out in the class that when we have a concentrated moment counterclockwise, the moment is negative. It's a downward jump. That's what it tells us. And if you use the notation that we had in the notes in the beginning, the by convention, that shows us that the moment that is applied here counterclockwise, which I put it there, it's going to bend the beam downward, putting the fibers underneath the beam in compression and the ones above the beam in tension. So this, we said this is a negative moment, vice versa would be positive. So Either way, we end up with a minus 3pl here at point A. Then as we move from left to right, again, we have to look at that equation. And I have the first segment here. In this moment, we have v of x is not zero like it was in previously w of x in the previous slide. So this time we can see that we have a sign. We have to look at the sign of the vx, and we also have to look at the magnitude of v of x. So the sign is positive and the magnitude, as you can see, it's constant there. That tells us that the slope of this moment, bending moment, is supposed to be positive and constant, which I put it here. If the slope is constant, it means it's a line, and then that line has a positive slope. That's what it tells us. So we are at this moment right here, and that means we have to go with along a line with a positive slope. And the slope, by the way, it's at every point, it is basically the value of the shear in that location. So for us, it's 2p. Uh, Now the question is, what's going to be the value right here when I reach this moment length L? So again, if you can look at this equation, in order to find the moment right there, we kind of need to take the derivative, the change, basically from this location all the way to there. So because the moment in point B will be the moment in point A plus that change that we are seeing it there. That means that we have to move this dx next to v of x, and then integrate the whole equation and find the moment. So basically, from that location to that location, integrate. And that means that the integral is the area under the curve, because we talk about this Vx. So the function here is that, it's constant line, horizontal line. So the integral will be, the change will be the area under this curve, which I kind of put it there with this yellow uh, rectangle. So easy to calculate the area, and then we apply that formula that we can calculate the moment at point B. Same thing as we move toward point segment BC. There is no moment, by the way, here, concentrated moment, to have any jump. So we only look at this equation, and that equation tells us that the slope right here is basically positive, as you can see here. I mean, the slope, the v of x, is positive, and the magnitude is zero. It's, pardon me, constant. So that's what we have it there. And then it means that the slope of the moment will be positive and it will be constant. Again, constant slope, it's a line. And by the way, the slope, we can see, we know the value here. It's easy to calculate, to look at the value. It's a constant value of p, the force P there. So again, we apply the same principle we did in this one. In order to find the moment right there, we assume we are supposed to get at zero, because there is no moment right there. So we are having it right there as we go. We calculate the integral, as we said, with the change, and that would be the area of this rectangle. And that will be the moment in C, will be the moment in B where we start, plus the change being the area of this green rectangle. I hope this simple problem it's introducing you very well to building the shear diagram and the moment diagram. If you do have questions, please let me know. Especially you can also write in the comments underneath, and if you have better ideas, also let me know about this. Have a beautiful day.